Good evening all. Last class we have completed increasing and decreasing. We will move to maxima and minima for this academic year. So maxima and minima, first we will definition of maxima and minima, and then we will find how to use that differentiation, that is first derivative and second derivative test, to find maxima and minima for the problems. So what is maxima or minima means? F be a function in the interval I. So I am going to define a function f in the interval I. So now f is said to be maximum. F is said to be maximum in that interval. If there exists a point C, I am going to take a point, any point C in that interval. F of C should be greater than f of x. So for all the value of x, I need to find among all the values, f of x value is greater means we can clearly say that this f is maximum and f of C is the maximum value. It is attaining maximum at the point C. Clear? Now second definition, minimum value. So f is minimum value means same interval I am taking. If there exists a point C such that f of C must be less than, comparing to all the value of x, f of x, that is comparing all the value of f of x, my f of C value is less value. That is, for example, any value in the interval we are taking, comparing to all the values, this f of C is less than all the f of x means we can say that f of x is the minimum, f of C is the minimum value. We can say that f is attaining minimum value. That minimum value f of C is the minimum value where C is the point of minima. Here f is extreme value means either f is maximum or f is minimum. Is it possible to find f is minimum or f is maximum means we can say that f is extremum. Next we will see the definition of local maxima and local minima. Now next definition, local maxima and local minima. So we are going to take a function f is a real valued function and C be a point we are taking. That C point is in the domain of f. We are going to say that the C is called the point of local maxima. When we can say means we have to find a point h. So h is the smallest positive integer, that is h greater than 0. If I am considering the C value equal to 5 means my h value is 0.1, smallest value, smallest positive value. So our interval that C minus h and C plus h will be 4.9 to 5.1, 4.9 comma 5.1. That is the interval C minus h to C plus h. Now I am going to select a value from all the value of x in this interval greater than 4.9, less than 5.1. All the points I am selecting and finding the value of that of the point. So that point is f of x means if the f of x among all the f of x, this f of C is greater value means we can say that clearly this f of C is the local maximum value, and local maximum value is f of C here at maximum attaining at the point of C. Now second case, local minima. C is called a point of local minima means there exists a smallest integer h greater than 0. Same interval I can take, same interval and h value also I can take. So I will get the interval 4.9 to 5.1. So in this interval f of all the value of this x, f of C is less than the f of x. F of C is comparing to all the values, f of C is less than the f of x value means this f of C is called local minimum value and it is attaining local minimum at x equal to C. This is the definition of local maximum and local minimum. Next we will see what is the point definition of critical point, then we will move to the first derivative test definition. Next definition, critical point. A point is C in the domain of a function f at which either f dash of x equal to 0 or f is not differentiable is called a critical point. That is, for example, a function f of x is f of x given, a function f of x given, what we have to find? We have to find the f dash of x, then we have to equate with 0. The corresponding x values we are getting from this equation are called critical points. Suppose f is not differentiable at x equal to 0 also, we can take it as a critical point. Now come to the first derivative test. Why we are using first derivative test means each and every time we cannot check the local maxima, local minima at every point. So we are using the first derivative test. What is the first derivative test means? We are going to define a function f. F is a function defined on open interval in I, open interval I, and f be a continuous function at the critical point C. If you are going to find that the function is defined at interval I and the critical point we have to find that critical point, the function must be continuous. Then first one, if f dash of x changes the sign negative to positive as x increases through C. For example, if my phi is the critical point, if phi is the critical point means left side of the point or left side of the phi are 4.7, 4.8 like that, right sides are 5.1, 5.2 like that. Now I am finding the f dash x value. So after finding f dash of x, if I am finding the value of f dash of 4.7, f dash of 4.8, f dash of 4.9, all the values, suppose it is negative, f dash of 4.7 negative, 4.8 negative, 4.9 negative. Similarly, right side of the point, for example, f dash of 5.1, f dash of 5.2, f dash of 5.3, everything is positive means the point, the sign changes to negative to positive means that point C is called local maximum. So f of C is the local maximum value. Same definition, if f dash of x changes the sign from positive to negative, in this case positive to negative. So if I'm the same point C equal to, we can take it as C equal to 5, left side of 5 are 4.7, 4.8, 4.9, right side of the 5 are 5.1, 5.2, 5.3, all these points. If f of 4.7 is positive, f dash of 4.7 is positive, f dash of 4.8 is positive, f dash of 4.9 is positive. Similarly, f dash of 5.1 is negative, 5.2 is negative, 5.3 is negative, like that is there. So I am taking the values from left side of 5 to right side of 5. So left side of 5, all the values, f dash values are positive. Right side, all the values are negative means the f dash sign changes to positive to negative means we can say that f of C is called local minimum. So local minimum value is f of C is the local minimum value. Third case, suppose in the both sides also same symbol, for example this side also positive, this side also positive, mean there is no change in the sign. So similarly both sides also negative also, f dash of 4.7, 4.8, 4.9 negative. Similarly f dash of 5.1, 5.2, 5.3 also negative means there is no changes of sign. So we have to declare that the point C is called point of inflection. That point C is called point of inflection. So point of inflection means we can say that there is no maxima, no minima. That point is neither maximum nor minimum. So we can say that that point is called point of inflection. Now same local maxima, local minima, we will use the second derivative test and we will prove that the second derivative test comparing to first derivative test, second derivative test is easy. Second derivative test. So f be a function defined on the interval I and I am taking a point C in the interval. Let f be a twice differentiable at point C. So f function f should be differentiated twice at the point C. If x equal to C, we are taking that point we are telling that it is local maximum means f dash of C equal to 0 and f double dash of C must be less than 0. F double dash of C is less than 0 means we can say that f of C is the local maximum value and at x equal to C the function attaining local maximum. Similarly, x equal to C I am taking f dash of C equal to 0 and f double dash of C is greater than 0 means I can say that f is attaining local minimum. The local minimum value equal to f of C, it is attaining at the point x equal to C. Suppose the third case, f dash of C also 0, f double dash of C also 0 means the second derivative test fails. That case what we have to do, we have to go back to the first derivative test and check whether the the function is changing positive to negative, that is f dash of C is changing positive to negative or not, or negative to positive or not. If it is changing positive to negative mean that is local maximum. If it is changing negative to positive mean that is local minimum. It's neither positive neither changing, this both also positive or both also negative mean that is point of inflection. Clear? Now we will move to the exercise problems. Exercise 6.5 5. First question we will see now. First question, it is given f of x equal to 2x minus 1 whole square plus 3. So we are going to find the maximum value, minimum value for this. If available maximum values, minimum values, we will find now. So we know that here, we know that 2 times x minus 1 whole square is always greater than or equal to 0. Now we can add any constants both sides. So I am going to add the plus 3 both sides. So 2x minus 1 whole square plus 3 greater than or equal to 3. So this is the given function. So f of x value is always greater than or equal to 3. So our our maximum value, there is no maximum value here. So we can write no maximum value. What about minimum value? Minimum value equal to 3, less than 3 it is not possible to get. So we can write that minimum value equal to 3, and there is no maximum value for the given f of x. Next question, this question number A, question A. Next question B. Next question B, f of x equal to 9x square plus 12x plus 2. So this I am going to factorize here. So I am going to factorize, or I am going to write as a, using completing square method, I am going to write as a perfect square plus some constant or some minus some constant. So to make that, we have to write this as a square, so 3x the whole square plus 2 into a into b. So 2 into 3x, 6x remaining 2. So I need 2 square. To compensate that, I am subtracting 2 square here. Then the remaining plus 2. So this value equal to a square plus 2ab plus b square, which is nothing but a plus b whole square. So 3x plus 2 whole square minus 4 plus 2, total value equal to minus 2. So clearly my f of x simplified to this some number square, some square minus 2 or plus 2 or some square plus constant or minus constant form. Now we can write usual method. We know that this 3x plus 2 whole square greater than or equal to 0. So I am going to add minus 2 both sides. So 3x plus 2 whole square minus 2 greater than or equal to minus 2. Now what is the minimum value here? So minimum value equal to minus 2. What about maximum value? As much as possible value of x, I can get largest value here. So we can conclude that no maximum value. This f of x has only minimum value, that minimum value equal to minus 2. Next question, question C. So question C, what is given? Same, f of x equal to minus of x minus 1 whole square plus 10. Now we know that already x minus 1 whole square is greater than or equal to 0. So we know that x minus 1 whole square greater than or equal to 0. I need a minus of x minus 1 whole square. So I am multiplying by minus both sides. Multiplying minus means inequality will reverse. So minus of x minus 1 whole square is less than or equal to 0. Now I need this minus of x minus 1 whole square plus 10. So I am adding plus 10 both sides. So minus of x minus 1 whole square plus 10 less than or equal to 10 now. So here the f of x is clearly less than or equal to some constant, that constant equal to 10. So I can find the maximum value. So maximum value of f of x equal to 10. As much as largest value of x, we will get the very least value, very least negative value. So we can say that no minimum value for this function. Clear? Now come to next question. So D question. So what is question D? H of x equal to, g of x equal to x cube plus 1 is given. G of x equal to x cube plus 1 is given. So this is a different question, an interesting question also. So we are taking the x value is very large value. So very large value of x, for very large value of x, our f of x is very large. If you are taking the very large value of x, substituting here, we will get the very large value, maximum value will come. Similarly, for very small value of x, f of x is very small. So, we cannot find the maximum value, minimum value for this function. So, clearly we can say g of x has no maximum as well as no minimum. G of x has no maximum as well as no minimum. The same problem we can use the second derivative test also, we can prove that. For example, see that how I am proving. So g of x is given, we have to find the g dash of x. So g dash of x equal to, it is 3x square. So we have to find the critical point. So critical point means g dash of x equal to 0. This implies we will get x equal to 0. So x equal to 0 is the critical point now. Now we will find the second derivative, g double dash of x. G double dash of x equal to 6x will come. So substituting this x value in g double dash, we will get 0. So I said already, g double dash is g double dash of c. G double dash of the critical point is greater than 0 means that is minimum. G double dash of c is less than 0 means that is maximum. But here g double dash of c equal to 0. So second derivative test fails. We go back to first derivative test. What is first derivative test? First derivative test is g dash of c must change the sign positive to negative means positive to negative means that is maximum, negative to positive means that is minimum. So our critical point is 0. So left side of 0 I can take -1. So substituting in the g dash, so g dash of -1 equal to this value, g dash of -1 equal to 3 into -1 square, that is equal to positive 3. The symbol is positive. Similarly, right side of c, right side of 0 I am taking. Right side of 0 I can take the point as 1. So g dash of 1 also equal to 3 into 1 square, that is equal to 3. That is also positive. So here the g dash of x, x passes through, x increases through the point c. X increases through the point, critical point c. The g dash of x is not changing the sign. It is both sides also positive. So we can say that that is the point of inflection. X equal to 0 is the point of inflection, and we can conclude that there is no maximum, there is no minimum. So that's why we are concluding that as much as large value of x, g of x is maximum. Similarly, as much x smallest value of x, g of x is minimum. So we can say that there is no maximum, no minimum for the given function g of x equal to x cube plus 1. So now come to question number 2. Find the minimum value and maximum value if any of the following functions. So first question, A question, f of x equal to modulus of x plus 2 minus 1. So we are going to find the minimum value and maximum value for this function. If it is possible means we will find it. So we know that modulus of x plus 2 is always greater than or equal to 0. So modulus of x plus 2 is always greater than or equal to 0. So we are going to add -1 both sides. So I will get modulus of x plus 2 minus 1 greater than or equal to -1. So whatever may be the possible value of x, the largest value of x, this value is always greater than or equal to -1. So our minimum value equal to -1. So what about the maximum value? As much as possible of largest value of x, we will get maximum value. So we can conclude that there is no maximum value. There is no maximum value for the f of x. Now next question, question B. So g of x is given, question B, g of x equal to minus of x plus 1 plus 3. So what is the value of x plus 1? We know that modulus of x plus 1 is always greater than or equal to 0. I need a modulus of minus of modulus of x plus 1. So multiplying by minus both sides, inequality will be reversed. Now I need to add 3 both sides. So what will come? Modulus of minus of x plus 1 minus of modulus of x plus 1 plus 3 is less than or equal to 3. So whatever may be the value of x, as much as possible largest value of x, the value of this g of x is not beyond the 3, that is maximum value equal to 3. Maximum value equal to 3. So if as much as possible largest value of x, we will get the more negative value. For example, if you are taking 1000 means minus of 1000 plus 3 minus 997 will come. If you are taking x equal to 10,000, x equal to 20,000 means we will get the largest negative value. So there is no possibility to find the minimum value. So we can conclude that no minimum value for g of x for any value of x. Next question. Question C. So C question given that h of x equal to sine 2x plus 5. So we know that the value of sine x is, maximum value of sine x is positive 1, minimum value of sine x is negative 1, as well as maximum value of sine 2x and minimum value of sine 2x also same minus 1 and plus 1. So we are using that here. We know that sine 2x is less than or equal to 1, greater than or equal to minus 1. I need sine 2x plus 5, so I am adding plus 5 both sides, minus 1 plus 5 less than or equal to sine 2x plus 5 less than or equal to 1 plus 5. Simplifying means minus 4 is less than or equal to sine 2x plus 5 is less than or equal to 6. So this is nothing but our h of x. So our h of x is greater than or equal to minus 4 less than or equal to 6. So minimum value of h of x equal to minus 4. Minimum value equal to minus 4. Similarly, maximum value of h of x equal to plus 6. So minimum value of h of x equal to minus 4 and maximum value equal to 6. Next D question. F of x equals to modulus of sine 4x plus 3. Modulus of sine 4x plus 3 is given. So we know that already. We know that sine 4x is greater than or equal to minus 1 less than or equal to 1. Sine 4x is greater than or equal to minus 1 and less than or equal to 1. So I need the 3 both sides. I am going to add 3. So minus 1 plus 3 less than or equal to sine 4x plus 3 less than or equal to 3 plus 1 or 1 plus 3. So simplifying this, we will get 2 less than or equal to sine 4x plus 3 less than or equal to 4. Now I need the modulus symbol. So I am taking modulus. So modulus of 2 also equal to 2 less than or equal to, this value is nothing but f of x and less than or equal to modulus of 4 equal to 4. Now what is the minimum value here? Minimum value equal to 2. Similarly, maximum value equal to 4. So minimum value of f of x is 2. Maximum value of f of x equal to 4. Next question. H of x equals to x plus 1. Here the restriction of x must be open interval minus 1 to open interval plus 1. So if I am going to find the very nearest value of 1, for example 0.9 is the very nearest value of 1 means I can find 0.99 is the very nearest to 1. If I am saying this is this point is very nearest to 1 means I can easily say 0.999 is nearest comparing with this point. Similarly, I can find the very nearest point of 1, that is 0.999 etc. I cannot identify that point exactly. So we can say that there is no maximum value for this function in this interval. Similarly, I cannot find the minimum value also in this interval. So I can conclude that no maximum. Similarly, as well as no minimum value for f of x, sorry, h of x in the interval minus 1 to 1. Suppose my interval is closed minus 1 and interval is closed plus minus 1 to 1. It is closed interval means we can easily identify minus 1 is the minimum value and plus 1 is the maximum value. So from this problem we can conclude that if the interval is open, the open interval, we cannot find the minimum value, maximum value at the end point for this function x plus 1. Clear up? Okay. Remaining problems, question number 3 onwards, we will use the second derivative test to find the local minima and local maxima in next class. Thank you.